So this section looks at something called an acid-base titration. Now it's important to remember that while acid-base titrations are the most common type of titration, we can actually do it with different types of reactions. Okay? Now what a titration is I'm going to have a burette. Now my burette is this thing right here. It's a long skinny tube that has measurements, and it allows me to tell how much of a solution I've added. Okay? Now in my burette, I've got a solution of a known concentration. The solution that I know the concentration of, I call my titrant. Down in the flask below it, this thing right here, that's my unknown. I call that my analyte. So what I'm going to do is I'm going to react my solution of known concentration, which is my titrant, and I'm going to use the amount that reacts to figure out the concentration of my analyte. Now the way this works is I have to know how the two solutions react. I need to know their balanced chemical equation. What I'm going to do is I'm going to add my titrant until the point where it has reacted exactly with the analyte. This is called the equivalence point. Now, what I'm going to do is I'm going to have to actually add something called an indicator. For most of my reactions, not all, but most. The indicator changes color. And this is going to allow me to know that the reaction is done. I want an indicator that changes colors at or near the equivalence point. Now, this actually has a different term all on its own. The point where it changes color is called the end point. Now, when I choose my indicator, I want to choose carefully, and I want to choose an indicator that changes color. Its endpoint is really, really close to the equivalence point. So here's the way my titration works. Here is my unknown solution, and when I say it's unknown, I just don't know the concentration. I call that my analyte. Up here in the burette is my solution of known concentration. I call that my titrant. I'm also going to add a couple drops of an indicator. My indicator is going to change colors to tell me when my reaction is done. So what happens is I start adding my titrant to the unknown. And initially what happens as I'm adding the liquid is I'll see a little bit of color change right around where the titrant is being added. But as I stir it or as I swirl it, that color change goes away. I'm going to keep adding titrant, keep adding titrant, keep adding titrant until the entire solution turns colors and stays colors. Now I want just the barest hint of a color. I don't want a dark color change because I want just a little teeny color change so that I can be as close to the end point as possible. If I have a really dark color change, I call that overshooting the end point. Okay. So here's the way titration reactions look. I'm carrying out an experiment to standardize a sodium hydroxide solution. So I want to know the concentration. Okay. To do this, I'm taking 1.300 grams of potassium hydrogen phthalate, which is this, which is abbreviated KHP. They also are nice, and they tell me the molar mass of KHP. Now here's the important part. They tell me that it's an acid and it has one acidic hydrogen. Okay? So I'm going to have KHC8H4OH reacting with potassium hydroxide +1 -1. It's an acid-base reaction. I know I'm making water. And when I make my water, I'm also going to have this K partner up with this compound, which loses an H. So it's going to be, let's make it K2C8H4OH. Now I don't really need to write this out. What I really need to know is, since I have one acidic hydrogen, one basic hydroxide, it's a 1-to-1 molar ratio. Okay? So I'm told that I'm dissolving my acid in water. Okay? I'm going to add phenolphthalein as an indicator so that it changes color. I'm going to titrate the resulting solution with the sodium hydroxide solution until the endpoint is reached. The difference between the final and initial burette reading is 41.2 milliliters of sodium hydroxide, and I'm reacting it with exactly 1.300 grams of KHP. Okay, so I know that I've got 1.3009 grams of this. I know that I've got 41.20 milliliters of this. I know that I'm trying to find the concentration of this. Okay? So, I know exactly how many grams of this I have, so let's start there. I always start with the thing that is my known, my titrant. So I've got 1.3009 grams. Instead of writing this whole thing out, I'm just going to call it KHP. I know, because the problem tells me, that I've got 204.22 grams of KHP for every 1 mole of KHP. Well, I don't want to know about moles of KHP. I need to make that go away. I want to find out about KOH. I know when I change from one element or compound to another, I look at the equation, 1-to-1. And that will tell me how many moles of KOH I have. So if I plug this into my calculator, I get 0.006371. I want to keep 1, 2, 3, 4, 5 sig figs. 1, 2, 3, 4, 5 moles of KOH. That is not my concentration. Concentration is molarity. Moles per liter. Well, I know I have this many moles in this many milliliters. Okay, so let's change that from milliliters to liters. I know that there's 1 liter for every 1,000 milliliters. So this is my volume. So I've got 0.0063701 moles of KOH for every 0.04120 liters. If I plug that into my calculator, I know that I've got 0.1546 moles per liter KOH. So now I know the concentration of my unknown because I know how much of my known it took to react with it. Okay? So take a second to solve example 14. They tell me that I'm trying to analyze waste material. It contains carbon tetrachloride and benzoic acid, a weak acid, one acidic hydrogen. So this is the acid I'm working with. Okay? They tell me that it's going to be weighed out. I've got that many grams of it. And I'm mixing it with water. Okay? I'm reacting that with NaOH. They tell me that I'm adding 10.59 milliliters of 0.1546 molar NaOH. Okay? They tell me that I've got one acidic proton here, so this H reacts with the OH to make water, and then I'm going to make NaC7H5O2. They want to find out, now this isn't just the H, it's the whole thing. They want to find out how many grams of this is actually in the whole mixture that had the weak acid and the carbon tetrachloride and the other stuff. And I want to find the mass percent of this compound in here. So start with your unknown, use your unknown, start with your known, use your known to figure out how many grams of this you have. Once you know that, calculate your mass percent. So here's the way this problem should have worked. I start with my known. I'm changing that to my unknown. So I know I've got 10.59 milliliters NaOH. I never like milliliters, so the first thing I do is I change that to liters. Once I know how many milliliters they have, I want to get rid of liters of NaOH. I want to know about moles. Remember, my molarity tells me I've got 0.1546 moles for every 1 liter of solution. Well, I don't want to know about NaOH. I want to know about HC7H5O2. By looking at the balanced chemical equation, I know that this is a 1-to-1 molar reaction. And I also know I want to find mass percent, so I want to find out how many grams of this is actually in it. So my last step, I need to change moles of benzoic acid, HC7H5O2, into grams. Well, I know that 1 mole is always equal to the number from the periodic table. I add up 1 plus 7 times 12 plus 5 plus 2 times 16, and I get 102 grams. I plug all of this into my calculator, and I get 0.166995 grams. I only get to keep 4 sig figs. So 0.166, actually, sorry, that 9 rounds that to a 0, rounds that to a 7. There we go. Okay, so that's how many grams of this I have. For mass percent, I take grams of the thing I have divided by total grams. And because it's a percentage, I multiply by 100. So I should get 47.47% benzoic acid in my released waste material. Okay?